Welcome, guys. Chapter 25, Section 3, The Evolution of a Star. All right, now you can see there's two life cycles here. If we take the top path starts with a stellar nebula. We'll probably just say nebula most of the time. All right, then we go to the yellow average star, red giant, planetary nebula, white dwarf, and maybe sometimes a neutron star. The other route is if stars are bigger and more massive. They go from the nebula to the massive star, the blue one on the bottom, then the red giant, then the supernova, and possibly a black hole or a neutron star. Those are the different progressions we're going to talk about. But we're going to also talk about why they happen. All right, evolution of a star. Yes, we used evolution. It means change. All right, we start with this nebula that's right here. All right, that is a nebula. And a nebula is a large cloud of gas and dust. That's what a nebula is, and we move on. Gravitational forces, so the gravity that holds us to the Earth, start pulling particles closer and closer together. Now, if you think about people walking around in blindfolds in a room, they would occasionally bump into each other. Now, let's say we take the size of that room, but keep the number of people the same, and we cut it in half. Wouldn't the people bump into each other more? And as we get smaller and smaller, the people are going to bump into each other more. And as items bump into each other, rub your hands together. You feel it's getting warm? That's causing friction, or friction causes that heat. When these particles bump into each other, they cause heat. Now, that heat causes the temperature to increase because of those collisions of those particles out there as gravity pulls them together. A bunch of collisions, we have a bunch of heat. This continues until 10 million Kelvin is achieved. Then fusion from hydrogen to helium happens. Fusion from hydrogen to helium happens. And that's what powers our sun and all other stars. Energy is left over when we have fusion from hydrogen to helium. And that energy is released as heat, light, and sound in our stars. When this happens, a main sequence star is born. So a nebula contracts. Temperatures go up, 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 up. When they reach a certain point, fusion from hydrogen to helium happen, and a main sequence star is born, and it continues to get energy by changing hydrogen to helium. Hopefully you caught I said hydrogen fuses to helium about 7 times. Now, we saw this slide yesterday. So how does it produce energy? Well, for hydrogen, you see them here. I'm going to put blue dots on them. For hydrogen, change into, going to put a black dot on it, 1 helium. The 4 hydrogen fuse and break down to 1 helium. Oh, problem is we've got, and I'm going to mark them green, 2 leftover protons. Those leftover protons, well, they are extra mass. That extra mass is converted to energy. And that's what escapes as heat, light, and sound in stars. And that process is called fusion. Fusion from hydrogen to helium. Okay? Now, a main sequence star to a giant. So how does a main sequence star change to a giant? Think about a car. Why would a car stop running? Well, let's assume everything keeps working right, but all of a sudden, put, and you slow down to a stop. The car stopped running because you ran out of gas. Okay? Running out of gas will cause the star to stop, or the car to stop running. A main sequence star is kind of the same way. They stay a main sequence star as long as there's hydrogen left to be turned into helium. So hydrogen's kind of like the gas. That's what's being changed into helium. It keeps converting. Now, when the hydrogen runs out, the core contracts. Well, if the core goes together, there's still all those particles. So we're going to have more and more and more collisions. If there's more and more and more and more collisions, what's going to happen to the temperature? Up, up, up. And that's all increasing because of the friction of the particles crashing together. So, main sequence star as long as there's hydrogen left. Hydrogen runs out, core contracts. Temperatures go way up. And because of friction, because the increase in heat, it causes the star to expand. Think like a popcorn kernel. Enough heat, and all of a sudden, poof, out it goes. Then, that is when it evolves into a red giant. The main thing is, when the hydrogen runs out, contraction, temperature goes up, and poof, it explodes out into a red giant. The red giant is the next sequence in our star life. And it doesn't go there until hydrogen runs out. Then all these things happen. Contract. Heat goes up. Boom. Explodes out into a red giant. All right. So now we have a red giant. These are actually Hubble Space Telescope images too. All right. The red giant happens at 100 million Kelvin. 10 times hotter than a main sequence star. All right? Now, at this level, remember how we turned everything into helium? Well, now helium is the gas, and helium is fused into carbon. So, just like before when we had all those hydrogen change into helium, now helium changes into carbon. And the red giant is so big that the outer layers are much cooler. Remember how we talked about red being the coolest color star? All right, that is evident here. Now, if any of you have been really thinking, the main sequence star changed when it ran out of hydrogen. When do you think the giant changes into something new? Is it when it runs out of helium? Well, that would make sense. It would follow the same pattern. So, a giant to a white dwarf. Let's see if we were right. When the helium runs out, the core contracts more. Woo! Goes down really small. What happens if the core contracts more? The particles run into each other more. If the particles run into each other more, what happens to the temperature? Goes way up. And a white dwarf is born. It's about the size of Earth. Our sun is about 1 million times bigger than Earth, and it shrinks to be the size of Earth. That gets really small going from a main sequence star to a white dwarf. All right, there's the comparison for you. And that is the end of the star life for a main sequence star. Okay? So, nebula contracts, temperatures go up. Main sequence star. Main sequence star turns hydrogen into helium. Does that until it runs out of hydrogen. Then it contracts. Temperature goes up. Boom! Red giant is born. Red giant starts turning helium into carbon. Helium into carbon. When the helium runs out, core contracts even more. Then the temperature goes way up, and we have a white dwarf born. Now, we just followed the top path on the previous slides. Now, we follow the bottom path. When stars are 10 times bigger, stages we just learned happen, but they happen more quickly and more violently. The differences that happen is when the core collapses, the outer portion explodes. This is the cause. That explosion causes the star to become a Supernova. All right. So the cause is the core collapses. The effect is a supernova is created. Neutron stars and black holes. A neutron star happens after supernovas collapse. So they collapse. They become 10 to 15 kilometers across and only have neutrons in them. Only neutrons. So remember, these stars we're talking about now, they were 10 to 15 times bigger than our sun. And now they're only 10 to 15 miles across. That's like going from here to Baldwin. So to be 10 times our sun, which can hold 1,000,000 Earths, to only 10 to 15 kilometers, there's been a huge change in size, hasn't there? Now, black holes happen when neutron stars' core collapses quickly. Black holes happen when neutron stars' core collapses quickly. So dense these black holes are that not even light can escape its gravity. Not even light can escape its gravity. That is pretty crazy. We cannot imagine what black holes are like, but they've tried to draw pictures and images. Now, this is an HR diagram. It talks about star brightness and temperature. 90% of all stars are main sequence stars. And the main sequence stars, you're going to see me circled in blue. The main sequence stars go right here. Now this bottom line, this is temperature. This side line, this is how bright they are. Okay? So with main sequence stars, when they're way over here, these red dots over here that I'm drawing all extra ones over here, these red dots over here, we're going to circle it. They are very cool. This end is cool. This end is hot. This down here is dim. And this is very bright. So this stuff I circled in red, they're very cool and they're very dim if we follow it over. Oh, these that I circle in blue way up here, they're very bright and they're very hot. Okay? So as you go up the main sequence, the warmer they get, the brighter they get. So let's look at it this way. As we go up, that green arrow, the warmer they get, the brighter they get. So our sun, this yellow one in here, is pretty average. It's kind of cool, kind of bright. It's pretty middling, okay? Now, there are some stars like, you're going to see me circle it in red, the white dwarfs. The white dwarfs are very hot, but they are not very bright. So they're quite hot, but not very bright. So they're not a main sequence star because they do something different. They're dim and hot. Normally when a star is hot, it is bright. Okay? We have another group that I'm going to circle in green. We have our giants and supergiants. The giants and supergiants are, again, a different group. They're very cool, if you follow it down here, but they're very bright, if you follow it over here. So supergiants are cool and bright. White dwarfs are dim and hot, and those are both abnormal. But main sequence stars, the cooler you are, the dimmer you are. The brighter you are, the hotter you are. And that's what we can know about the HR diagram. All right? I hope to discuss this with you in person. Now, to recap, we can watch this YouTube video, but to save time, I am actually going to post this on your Google Classroom as well.